So last class in transformer, we were discussing the parameters of the transformer winding and how the losses are represented in the winding. So we have discussed that the core loss and the copper loss as well as the leakage loss are represented by different parameters in the transformer winding. And since the transformer winding is of two winding, so it's better to transfer one side into the another so that the calculation become easy. Then we can obtain the impedance in the primary side or the secondary side referred from one side to the another to find the equivalent impedance of the transformer. So from here on we will start for today's class. So due to the all the losses that we have taken into consideration for any practical transformer, now the phasor diagram of the transformer will improve from what we have discussed from the ideal case. So earlier we have discussed that the primary current of the transformer will be equal to the no load current, and it is equal to I mu in the ideal case of the transformer. Then we have discussed that now one more term will be added. So I mu plus IW will be the losses included in the core. Then we have discussed that these component, which is the no load component of the transformer, then we can add one more component, that is I2 dash. So I2 dash is basically the component of the current which is due to the load present in the transformer. So when you are loading the transformer, there will be a current I2 flowing, and in order to counterbalance the flux, to keep the flux in the core to be constant, we will be having one current which is I2 dash, and this current will be added in the primary current of the transformer. So this we have discussed in theoretical. So we will draw the phasor diagram. So the flux which is there on the x-axis, and you will be having the voltage V2 which will be lagging the current I2 by an angle phi 2. This is the load power factor angle. So here you have the load power factor angle. So the current I2 you can take anti-phase, so you will get I2 dash here, right? And you will be having a no load component of the current I0, and together the sum of that you can form as I1. So you can draw the phasor diagram either taking the lagging power factor condition, which is the most general one, because most of the load in industries you will get from the lagging power factor, and then you can redraw the circuit for the leading power factor or the unity power factor condition, taking all the losses into account either in the primary circuit or in the secondary circuit. So I1 R1 will be the loss in the primary resistance, I1 X1 is the loss in the leakage of the primary winding. Similarly, I2 R2 will be the loss in the secondary winding resistance, and I2 X2 is the loss in the secondary winding leakage reactance. So using the KVL equation, you can now write the KVL equation. V1, which is the supply voltage, is equal to E1, that is the induced EMF, plus one more term will come I1 Z1. Now here V1 equal to E1 is generally the case of ideal transformer when this component is 0. Then you do not have any loss, which we have discussed in the case of an ideal transformer. But when you have a practical transformer, your all losses will have to take into consideration. So the impedance Z1 will be the sum of R1 plus JX1. Right? And similarly, if you write on the secondary side of the transformer, then you will have induced EMF E2 is equal to V2, that is the terminal voltage, plus I2 into Z2, where Z2 is basically the total loss taking into consideration the resistance and the reactance. Now, in order to solve this problem, it will be better if you transfer to one side. So Z equivalent, if you try to find out, on the primary side of the transformer, you keep the primary constant and take the secondary on the primary side. So Z1 plus Z2 dash, and then you can solve all the numericals easily. So this we are going to see in more detail after few slides. So let us see that. So today, let us first discuss the voltage drop in a transformer. So what is the voltage drop? So under the no load condition, you will be having V1 normally equal to I1, because the no load component of the current I0, which is the no load current I1, is about 1% of the full load current that we have discussed in the important point to be noted. So the current I1 is very small, and hence the drop can be neglected in the primary winding, and as a result your V1 and E1, that is the supply voltage and the induced EMF in the primary winding, you can take it to be equal under the no load condition. So if you have any transformer, so in transformer, if there is a primary winding which is connected with the supply voltage, so this is equal to V1, and your secondary you are keeping at no load condition. So what is happening? All the losses that is there in the winding we can neglect, and hence V1 is equal to E1, because your I1 is very small, and E2, which is the induced EMF on the secondary winding, is basically K times E1, where K is the transformation ratio, which you can take as N2 by N1. So N2 by N1 is the transformation ratio depending upon the number of turns, and since V1 is equal to E1, you can write E2 is equal to K times V1 directly. So you can find the induced EMF on the secondary side of the transformer knowing the supply voltage V1 and the transformation ratio. So we can just represent our E2 under the no load condition as something where we can include a zero term and for representing the no load condition. So let us see what has happened when the transformer is under loaded condition. So transformer is under load condition. So you have connected a load, and I assume that the load is inductive in nature. So obviously the current will lag behind the voltage by certain angle. So if I take the V2, that is the voltage in the load, as the reference quantity, so I take the V2 as a reference, then we can take V2 here, which is the reference at 0 degree. So this is at 0 degree of your axis. So here you can draw the axis. So this side is your minus X and this is Y. This is minus Y, right? So you will be having V2 as the reference, and current I2, which is drawn by the load, due to the inductive nature there will be a lagging power factor of minus theta, right? So theta, there is a lagging power factor angle between the voltage V2 and the current I2, because V2 we have taken is at reference. Now we know the equation that E2 is equal to V2 plus I2 into Z2. Now if you take all the quantities on the secondary side of the transformer, that is all the primary parameters to the secondary side of the transformer, then basically we are going to deal with Z02. So Z02, which is the total impedance on the secondary side of the transformer, is basically R02, total resistance on the secondary side, plus J time X02, that is total reactance on the secondary side, and this is the combination of the primary side and the secondary side. So obviously on the secondary side, if you try to find out what is the voltage drop in the resistance, so you will be having I2 into R02, because I2 you have here, and you know that for a DC quantity, which is the resistance, obviously it will be in phase with each other. So current drop I2, voltage drop I2 R02 will be in phase with I2. So we have drawn it in this way, and I2 X02, which is at 90 degree from here, uh, is the drop in the reactance. So if you have an ordinary circuit concept, this is your resistance and this is your reactance, and you have a voltage which is E2 here. So you have to get V2 on this side. So the current what is flowing is basically I2, and this total resistance is R02 and X02. So the drop R02, I2 into R02 is the drop in the resistance, I2X02 is the total drop in the reactance. Hence we can get the vector sum of the drop in the resistance and the reactance as the impedance. So you have the drop I2Z02, that is the total drop in the secondary side of the transformer, which is drawing a current I2, and the net impedance is Z02. Then your equation E2 is equal to V2 plus I2, and here you will be having Z02 because that is the total impedance on the secondary side of the transformer. So you will be having the vector sum of V2 and I2Z02 as equal to E2. So this is your E2 line which you have drawn. So you have obtained the secondary induced EMF. Now what we have to obtain is the voltage drop in the transformer. So now this vector diagram, if we just elongate on the x-axis line, so if we elongate on the x-axis line and we just do some manipulations, like you have I2R02, you just resolve it on the x-axis component and the y-axis component. So here you have the power factor angle theta, so this angle will be also theta, so you will be having theta here, right? Then I2R02 will be resolved on the x-axis as I2R02 cos theta in this direction, and you are having your I2x02 from here, right? This is your I2x02 line, this one, so it is at 90 degree, this one, right? So these component of the current you can also resolve on the x-axis and the y-axis component. So you can resolve it on the x-axis as well as the y-axis. Basically we will be requiring the x-axis data, so that we are going to see. So the approximate voltage drop, so we are using a term approximate because it will be not totally equal, we'll have approximate. So approximate voltage drop in the transformer will then in that case will be I2R02 cos theta plus minus I2x02 sin theta. So we have used a sign plus minus, considering that plus will be for the lagging power factor condition and minus will be for the leading power factor condition. Because for the lagging power factor and leading power factor condition, you have to draw the phasor diagram appropriately and try to find out. However, on obtaining the equations, we'll get this equation for the voltage drop. So I2 basically the secondary current which is drawn by the load of the transformer. So you have connected a load on the secondary side, which I2 is the current, and R02 and X02 is the total reactance, resistance and the reactance on the secondary side, where phi is the angle between the voltage V2 and I2, that is the secondary voltage and current. So you can get the approximate voltage drop as I2R02 cos theta plus minus I2x02 sin theta. Now if the same thing you do it on the primary side, then your equation will be I1R01 cos theta plus minus I1x01 sin theta. So it will not matter whether you are solving from the primary side point of view or the secondary side point of view, and the answer will come the same, because we have obtained the equivalent resistance on the primary side and equivalent reactance on the primary side, and the net current is I1 on the primary side. Here we have taken R02 and X02 as the total resistance and the reactance, whereas the current is I2. Then what is the percentage voltage drop in the secondary? So the total voltage drop is I2R02 cos theta plus minus I2x02 sin theta. If you divide it with the no load voltage on the secondary side, which will be again equal to E2, right? Because when you do not have any load connected on the secondary side, then your current I2 will be 0. So I2 will be 0 under no load condition. Then the drop I2Z02 will be 0. So your V2 will be equal to E2 under the condition of no load condition. So you can take the denominator of this quantity as the reference as the no load quantity. So you can represent this into simpler form as VR cos phi plus minus Vx sin phi, where VR indicates the resistive percentage drop. So that is equal to your I2 R02 divided by the no load voltage into 100, or Vx is the percentage reactive drop. So I2 X02 by the no load voltage. So this is the simplest form and the approximate form of representing the drop in the transformer, where VR indicates the percentage resistive drop and Vx indicates the percentage reactive drop in the transformer. So if you want to solve this problem from the secondary aspect, then you refer all the quantities on the secondary side and try to determine R02 and X02. And if you want to solve the problem from the primary side, then you take R01 and X01. Only thing you have to consider that when you are referring the quantity from one side to the another, the current value should be taken from that side. So if you are referring on the primary side, always you have to take the current on that particular side, that is I1. So X01 will take a current I1, R02 will take a current I2, and if you are taking X02, you take a current I2. So these you have to take care when you are trying to find the voltage drop in the transformer. The next topic and the most important topic in power transformer or any transformer is to obtain the equivalent circuit of the transformer. So experiment number 10 that we are doing in the lab, we are obtaining the parameters of the equivalent circuit, and here we'll discuss the theory of that. So let us see that. So why the equivalent circuit is necessary for any particular transformer? So equivalent circuit is basically a diagram in which the resistance and leakage reactance of the transformer are imagined to be external to the winding. So basically what is happening, if you see, this is the core of the transformer, right? This is the core of the transformer, and you have the winding, and the total winding is submerged in the tank of the transformer. So this is the outer tank of the transformer. So outer tank of the transformer and the winding is brought out with the help of bushings in the transformer, right? So nothing is visible inside the transformer, only we can see the tank of the transformer and we can see the bushing of the transformer, which are the carrying the winding terminals. So if certain thing is happening inside the transformer, it is very difficult to do any type of analysis. So it is better to draw the equivalent circuit of the transformer using the terminals of the transformer, which is accessible. So for that reason, we are trying to obtain the equivalent circuit of the transformer. So equivalent circuit diagram of a transformer will then include what are the quantities. So if you remember, we have started our discussion from ideal transformer and then slowly moved to practical transformer, right? So in the ideal transformer, we have assumed that all losses are zero. So we have taken that all losses are zero in the ideal transformer, and practical transformer we have included all losses, right? So if we consider a two winding transformer which is ideal in nature, so this is your ideal transformer. This is your ideal transformer which is not having any losses. All losses will be zero. If you see the central line, we have drawn some central lines, parallel lines. So these represent the core. So if you have lines drawn, then it is the iron core or something we call CRGS core. If these lines are not drawn, means the lines are not present, it means that this is a air core transformer. Means there is no core and the transformer is air core, right? So obviously the representation of two winding transformer, so this is the winding number 1 and this is winding number 2. So winding 1 and winding 2 are placed in the close proximity to represent a ideal transformer having no losses. And now for a practical transformer, whatever the losses we have, we will add external to the ideal transformer. So this side external on the primary side and this type external on the secondary side. So we have seen that the no load component of the current I naught is basically the vector sum of I mu, that is the magnetizing component, plus the core loss component, right? And this no load component of the current is being given by the supply voltage V1, which is used to establish a flux in the core of the transformer and to give the core loss. So that is the hysteresis loss and the eddy current loss. So the V1, which is the supply voltage, is responsible for production of flux in the core, which is represented by X naught. So X naught is basically used to establish the flux in the core, which is represented by a inductor X naught. The current that is drawn by the inductor or to magnetize the core is I mu, that is the magnetizing component of the current. The component IW is responsible for the core loss. So core loss in the transformer, you have hysteresis loss and the eddy current loss, that will be represented by IW. So core loss is the summation of hysteresis loss plus eddy current loss. So we'll take our discussion further. Here the flux phi represent the loss due to the reactance X naught, that is, sorry, flux is used to produce the flux in the core due to the supply voltage V1, which is the magnetizing component of the current I mu, and the resistance R naught represent the core loss, that is IW. Now the vector sum of the current of IW and I mu is the no load component of the current, and you know that the no load component is 1% of the full load current, so it is very less, the no load component. Now the loss in the transformer due to the copper loss is represented by R1, and the loss due to the reactance or the leakage, so this leakage will be represented with X. So X represent the leakage drop in the transformer, and this leakage is only on the primary side of the transformer. So the total impedance Z1 on the primary side is the sum of R1 plus X1, and these are the vector quantities because there is a complex in nature. So your current I1, which is the total current on the transformer, is basically I naught, that is the no load component of the current, plus I2 dash. So the current I2 dash, which is the current due to the load condition of the transformer. So here we have connected a load on the secondary side of the transformer. So you will be having a current I2 dash here, right? So the current which was flowing I1 here is the summation of I naught and I2 dash. I naught is the current which is drawn by the shunt parameter. So shunt means parallel. So these two are shunt parameters, and I2 dash is the current which is entering to the ideal transformer. So this I2 dash depends upon the load. So if under the no load condition, your I2 dash will be 0 because your I2 will be 0. Now if you have a load on the secondary side of the transformer, so V2 is the secondary terminal voltage and E2 is the secondary induced EMF, whereas E1 is the primary induced EMF. On the secondary side, you have the loss R2, that is the resistance on the secondary side, and X2, that is the leakage drop on the secondary side. So the current I2 is flowing on the secondary winding, which is taken by the load of the transformer. The Z2 is the total impedance on the secondary side of the transformer. So phi 2, if you see, this is the phase angle between the voltage V2 and the current I2, right? And if you take the phi 1 angle, this is the angle between the voltage V1 and the current I1. Okay, if you take phi naught, that is the no load power factor, that is the angle between the supply voltage V1 and the no load component of the current I naught. So in this equivalent circuit of the transformer, all the parameters are represented for any practical transformer, and the current and the parameters are shown. So our aim basically will be to conduct certain tests so that we can obtain this parameter R1, X1, R2, X2, R0, X0. So these parameters have to be obtained from the terminals of the transformer. So these are the terminals of the transformer. So how do we do certain testing so that we can obtain the parameters appropriately? Okay, so that we are going to see. So now we will be obtaining the equivalent circuit parameters by doing certain tests. So let us see the secondary circuit first. So we are taking the secondary circuit having resistance R2, reactance X2, induced EMF E2, which is producing a voltage V2 on the load. ZL is basically the load impedance. So ZL is the load impedance, and I2 is the current which is taken by the load. Z2 is the total impedance of the circuit parameter R2 and X2. Please indicate here Z2 is different from ZL. ZL depends upon the load impedance, Z2 depend upon the parameter. So now if these particular quantity are referred to the primary side, means this is the secondary side of the transformer. If you want to take this on the primary side of the transformer, what will happen? So if you have taken the primary side of the transformer, then the load impedance ZL, you have to divide it with K square. So you take K value, that is the transformation ratio of the transformer, that is N2 by N1. So N2 by N1 is the transformation ratio, and the load impedance ZL is taken on the primary side by dividing ZL by K square. The voltage V2, which is the secondary voltage, is divided with K. So that is the transformation ratio, because you have V2 by V1 is equal to N2 by N1 is equal to K, right? And this is equal to I1 by I2. So these ratio will be useful to take the quantities from one side to the another. And now make a special note here that we are dividing with K square here, whereas we are dividing with K only here. So do not make a confusion and divide it with K, the load impedance. So load impedance is divided with K square, and the secondary voltage is divided with K. Also, the resistance and the reactance both are divided with K square to take it on the primary side. Then the current I2, which is in the secondary side, will become I2 dash on the primary side of the transformer. So the current will be I2 dash, and the voltage E2 dash will be equal to E1. So the induced EMF on the secondary side will become E1 on the primary side of the transformer, because E2 dash is equal to E1. Now we draw the equivalent circuit of the transformer taking all the quantities on the primary side. So this we have taken all the quantities on the primary side of the transformer. So we will not touch the primary parameters. So primary parameters will be R1, X1, R0 and X0. That will be as it is, representing with the voltage V1, current I1 and the no load current I0. So this will be as it is. Only thing is that we are taking the secondary parameters on the primary side of the transformer. So load has become ZL dash, voltage VL has become VL dash, the impedance, all this resistance and the reactance has become Z2 dash, okay, by the appropriate transformation with the help of transformation ratio. Then if you observe here, the current I1, that is the primary current, here you apply the KCL equation, Kirchhoff's current law, that is in the junction, this one. So I1 will be equal to I0 plus I2 dash. So I2 dash is the current which is flowing on the other part of the winding. So this is basically the current flowing through the load, right? And if you observe here, we have taken E1 is equal to E2 dash. So if you take this as the transformer, you have a two winding transformer. So this side you are having E1 and this side you have E2. So when you are referring this E2 on this side, so you will be having your E1 is equal to E2 dash. That is referring the secondary voltage induced EMF on the primary side of the transformer. So appropriately we have to obtain this circuit so that we can represent all the quantities into a single circuit point of view. So there is no transformer here. If you see it, there is no transformer. So it is entirely a circuit which is basically a RLC circuit, right? So sorry, RL circuit. There is no capacitor. Only thing is that capacitor can have here only in the load condition. So your ideal transformer, which is basically not having any losses, has now gone. We do not want to include this transformer in this equivalent circuit of the transformer. The equivalent circuit of the transformer has become simple now, and it will be easy to do all sort of calculation. So further, we can further simplify the equivalent circuit of the transformer. So how we are simplifying the equivalent circuit, so that we are going to see. So here you can see that this no load component of the current I naught, which is basically 1% of the full load current, if we take this here and we move this part of the circuit this side, so we can easily add these two components because this is disturbing. So since the current I naught is very less, we can easily move the component of the shunt parameters in this side. So that we have done. So we have moved the shunt parameters from here to this side. Why we have done? Because the no load component of the current is very less, so you can easily move this side and take all these parameters into series. So it will be easy to obtain the series equivalent circuit. Now the primary parameters and the secondary referred parameters has come into series thing, and the shunt parameters are the no load parameters of the circuit. So this one we can easily represent it with a single resistance and single reactance. So the resistance has become R01 plus R02 dash, and this has become X01 R1 plus R2 dash. This is become X1 plus X2 dash. So only one resistance and one reactance we can get, which is this one. Okay, so we have got a simplified circuit, and since the current is less, so we can neglect this part of the circuit to further simplify, and hence your current I1 will be equal to I2 dash. So whatever the current was flowing, so this is the most approximate equivalent circuit of the transformer, which is having a voltage V1 on the primary side of the transformer and the load ZL dash on the secondary side of the transformer. So you are having basically the impedance Z01 on the primary side of the transformer on the seat. So the most equivalent circuit of the transformer, most approximate equivalent circuit, is generally including a resistance and the reactance in series with the transformer. So under the no load condition of the transformer, if we neglect this under the no load condition, so basically the equivalent circuit of the transformer V1 will be equal to R01 plus X01. So this is the most approximate and the simplified form of the equivalent circuit of the transformer. However, to make the calculation appropriate, we will be going and find all the parameters individually. So the total impedance between the input terminal, let us find. What is the total impedance between the input terminal? So if we see from the input side, that is the V1 side of the terminal, so if we see it, what impedance do we get to find the Z equivalent? So that we see. So Z equivalent, if you are trying to find, then it will be equal to Z1, that is the impedance of the primary side of the transformer. So here you have the Z1 quantity, and you have something which is parallel, that is Zm, that is the magnetizing component. Then you are having one impedance Z2 dash, right? That is referred from the secondary side of the transformer to the primary side, and then you are having a load impedance ZL dash. So that is referred to the primary side. So the total impedance seen from the primary winding source is basically Z1, and that is the summation of the parallel quantities of Zm and parallel with the summation of Z2 dash plus ZL dash. So these two will come in series, and that will come in parallel with Zm, which will come in series with Z1, and then you can get easily the Z equivalent of the total transformer winding parameters Z equivalent seen from the primary side of the transformer, that is the input side of the transformer. Then you can find what is the input voltage. So you know that input voltage V1 is basically I1 into Z equivalent. So our circuit now will reduce from a single source V1, which is drawing a current I1, and you are having an impedance which is Z equivalent. So Z equivalent is basically the total impedance of the circuit that you have obtained seeing from the input terminal side. So these you can obtain knowing all the parameters. Then you can establish a relationship between voltage V1 and the current I1. So if V1 is mentioned to you and Z equivalent you are finding, you can easily find what is the current drawn by the primary side of the transformer, that is V1 by Z equivalent. So V1 by Z equivalent is the total current that is drawn by the primary side of the transformer. Right? Now the question of obtaining the parameters of the transformer will come, and that we will be discussing under the topic transformer testing. So what are the transformer tests you have to obtain the shunt parameter of the winding, that is R0 XM. So this represent the Zm value, and this you have the total impedance that you have taken in the circuit from the series parameter. So Zs and Zm, that is the series parameter and the shunt parameters, will represent the losses of the transformer, and that we have to obtain from the transformer testing. So if you see, this is the winding of the transformer, and if the terminals are coming out here, so you have to do all the testing on the terminals of the transformer, so that for this particular winding and the core you can draw the equivalent circuit of the transformer. So these core will have certain losses that you have represented with R0. This core will establish the flux, which is you have represented with XM, and the winding, which is represented with the resistance and the reactance, that you have represented with R and X. And if you are connecting any load here, so that you are basically connecting a load on the secondary side of the transformer, and we have to obtain these equivalent circuit parameters doing certain tests that we are going to discuss in the next class.